So when I actually give quizzes in class, the way it's going to work is you'll see me. I'll have my pile of papers ready to go. You'll see if I have 3 problems on there, I'll just write up on that. Who knows if they actually have ink in them. So you'll see problem 1, problem 2, like let's say out of 10, out of 15, out of 25, and then you'll see plus 50 in a category called attendance. Right? So the quizzes, the objective of them is to simulate a test setting without having a profoundly negative impact on your overall score. So the fact that you're here is half of the credit on the quizzes. So you go, you're going to be honest with yourself about what it is you actually know. You can identify what it is to study, and then by the time you turn around the exam, it's giving you a couple of practice opportunities. Plus that, those opportunities with the pressure are invaluable. The other thing, a couple students were asking questions about what to go on the quiz. That there's actually a good engineering lesson to be learned from that. I said phrase "better is the enemy of good enough." We're engineers. We like to think through problems, and we're creative. And we go, I want to try this and try that, and do like 20 other things. Or we often think there's no way this problem can be this simple. Sometimes if you add a bunch of bells and whistles, but it doesn't do the thing that the customer wants, then have you actually designed something? No. Ultimately, you got to design what the customer is, or not the customer is, what the customer wants. So that's when people I feel like are overthinking the problem in a very engineering way. I'll say better is the enemy of good enough. I just want exactly what the TGO says. You know what I'm saying? So, but that's very normal. That's not an insult. That's just life lessons. So, section 2. So the last section we talked about the fundamentals of what a computer architecture is, what a computer organization is. We talked a bit about machine instructions, assembly instructions, what a data path and control is, kind of basics of memory, and then we went into this concept of computing performance. And so you learned about Amdahl's law, and you learned that it's just speeding up one section of the computer doesn't speed up everything. And now we're actually going to start going down into what these computer sections actually are. So before we get into any kind of code, everything eventually goes through the computing arithmetic, through the arithmetic logic unit. Did you guys learn about ALUs in 235 at all? No one remembers 235? Okay, so an arithmetic logic unit is a device that performs some sort of arithmetic based on a set of control signals that come into the ALU. 2 inputs, and in this case, that's what we're going to be discussing in the ALU in MIPS, and then produces some sort of output, an overflow bit, valid bits. There's also going to be a branch instruction where using the device called a comparator, which we'll discuss in this section. So we want to, first of all, what is the idea of arithmetic? So I've included a quote here from Thomas Hobbes. Those of you familiar with the comic strip Calvin and Hobbes, they're actually based off of 2 philosophers named Calvin and Hobbes. And so Hobbes, the original Hobbes, in 1656, discussed the idea of computation as, so here's his quote, by ratiocination I mean computation. Now to compute is either to collect the sum of many things that are added together, or to know what remains when one thing is taken out of a number. So, and if any may add multiplication and division, I will not be against it, seeing as multiplication is nothing but addition of equals to one another, or division nothing but a subtraction, right? So if you have 100 divided by 25, right? What that actually means is how many times can I subtract 25 from 100 and still have something there? So 25, 100, 75, I still have something there. 75 minus 25 is 50. I'll go up to 2. 50 minus 25 is 25. And 25 minus 25 is 0. So that gives you 4. Okay? So the reason why I include this quote is because that's what's actually physically going on inside the arithmetic logic unit. What we're going to learn in this section are the physical details of what happens when you send code to this arithmetic logic unit. So ALUs, as you recall from what you just wrote up, is actually a computer organization. You cannot manipulate, you cannot physically change the ALU with code. But by using the computer architecture, you can design code to make it run efficiently and do what it is that you want it to do. So this is an example of a machine. So the machine instruction is actually this, right? So we have our assembly instruction. So what's going on here in MIPS, and we'll learn about the actual format of the instructions in the next section, but basically what's going on here is we have two 32-bit values that are stored in saved registers S1 and S2. And there are 32 registers, and the save registers start at register 16. So S1, so S0 is register 16, which means S1 is 17. So this value here is actually a register address indicating S1. So we're going to the register, we're getting the value out of this register here, and then we're putting it onto the inputs from the register. So we're getting two inputs to the ALU. So then you see here, this is S2. So this is 16 plus 2, so that's register 18. We're getting that value. And then we're performing some kind of function inside the arithmetic logic unit. So there's two topical guide objectives later in this section where we actually have a value coming from the ALU controller, which is manipulated by both the opcode, this 6-bit value here, and the function here, which is the last 6 bits. So if it's 0, 0, 0, 0, 0, what that means is it's a register type instruction. So we're going to learn this in the next section as well. But basically what a register type instruction is you take two register values, perform some sort of operation in the ALU, and then return it to a third register. So that's why T1, here we'll learn this more in the next section, but T0 is register 8. So you can see register 8 here. So you're adding, they have wrong code here. That should be T0. T0 is that value there. So T0, so I'm adding these two values here. So 0 is an R-type instruction, and 10000 or 20 hex. Oh, you all learned binary to hex conversion in 235, right? Okay, so there's a lot of nods there. So when you see it in the MIPS green sheet, you'll see 20 hex. This means this is a register type instruction, and this means I'm doing addition. So then this is where your architecture is. So then we send all this information to the arithmetic logic unit, and it's going to do a bunch of things. And we're going to learn how to actually perform different types of addition today. And then we're, in this case, you got I-type, integer type instructions. How do you actually take 2's complement values and physically perform addition inside the arithmetic logic unit? How can you use that to perform subtraction? How can you then use multiple additions, as Hobbes was talking about, to perform multiplication? So 9 times 8 is really just 8 plus 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 8, right? So that just comes out to 72. So it's, what's actually physically going on is it's 8 plus 8, then 16 plus 8, then 24 plus 8, then 32 plus 8, and so forth. So because it's storing that, physically storing that value. So that the importance of understanding this for the advanced digital system is you should physically know the details that are transparent to the programmer, so that way as an engineer or a coder, you can design your code so that way it understands those system attributes that contribute to its logical execution. So before this, we want to get into the actual 32-bit value in MIPS. So as you recall, in reduced instruction set architectures, they have a fixed instruction length and a fixed bus length, right? Recall that from section 1. In MIPS, all these values are 32. All the instructions are 32 bits. All the values that are put onto buses are 32 bits. So in this case, we want to if we're just doing the integer values, we want to represent the full range of what we can represent before we get into something called floating point, which is these are 32 values, 32 bits, and so the top one starts with a 0 and it's all ones. So in MIPS, if it's a signed integer, that means the first bit represents the sign of the number. So in this case, 0 and then a bunch of other ones. It represents 2 to the 31 minus 1. And the reason, so the reason it's 231 is because we have 31 ones here, right? But it's the same thing, right? So if this is our first bit, it's 2 to the 1 minus 1, which is equal to 1. This here is 2 to the 2 minus 1, which is equal to 3, and so forth. So that's how you get 2 to 31 minus 1. Here, we perform what's known as 2's complement. So you have 1 is the negative number, and then all zeros is your maximum negative number that you can represent. So if it starts with a 1 and it's all zeros, the actual value is negative 2 to the 31. So this is the full range of numbers that can be represented in this architecture. And so just as a review, when I first taught this, students were really struggling with the concept of signs, so I updated it, included this as the topical guide objective, that the most significant bit in MIPS is used to represent the sign of the number. Yes?
If we saw that as a question, would you want the full binary representation like every...
If you get that, well, you'll have the type of question, it'll come out in either questions like this where I'm saying do some sort of subtraction, or more than likely when we go into the concepts of floating point addition later in the section, how do you actually represent the IEEE 754 representation? Which values represent the exponent, which represent the actual mantissa, which ones represent the remainder, and the sign bit. So you'll actually see some kind of, so how do you actually represent infinity? So these are, I should note here, and we'll go into this in more detail later in this section, these numbers are essentially positive and negative infinity. If you're doing calculations where your numbers are getting this high, you've done something probably very wrong. And later in this section, I think that, yeah, this is the section we talk about signs and Gandhi and everything like that. We'll go over where that kind of mistake goes horribly wrong in video games. Right, so here, performing 2's complement, so you all remember what 2's complement is? See a couple of no's there. So basically the idea is that, let's say you have 7, you want to get negative 7, right? So you have a sign bit, and then we'll just use 4 bits to represent the number, right? So then what we're going to be doing is you flip all the numbers, and then you add 1. So this is the 2's complement of 7. So down here, what we're seeing is negative 6. So what happens is we have 0, 0, 1, 1, 0. That's 6. Then we flip all the bits, and then add 1. So if you look here, you see this 1, 0, 1, 0 is where that comes in. And then what would end up happening is if you represented it as six bits, for example, then it just becomes and then this all just becomes the sign extension. So in this example here, it's not a topical guide objective, but it's an example question. I just put it here as a small example to demonstrate the concept of 2's complement. At 7 and negative 6, what ends up happening here is you get the carry bit. You get this becomes 0, this becomes 0, that becomes 0, that becomes 0, that becomes, and so forth, right? It just keeps carrying. So what ends up happening here is that you're just left with a 1. And then when the carry bit goes away. So if you recall, and let me scroll back up here. If you recall here, we had this concept of flags. One of the flags that's going to come out of the arithmetic logic unit, as we'll go into more detail in this section, is the actual carry bit. Does this actually produce a carry bit? And then you will actually use that carry bit to compare with the sign bits to determine whether or not certain operations that you need to do. And that carry bit is often called the overflow. which is topical guide objective 2.3. So overflow occurs when the result of an operation cannot be represented with the available hardware. So, yes?
For the subtract 6 from 7, is it supposed to, so the 6 is negative, so is it
Correct.
supposed to be subtraction or addition?
What? I'll let you guys answer that question. What does the question state? Subtract 6 from 7.
Right. But it shows
All right. All right, you know what's actually going on, right?
Okay, so I
Yeah. I understand what you're saying, but subtract 6 from 7. Any other questions? All right, so overflow occurs when the result of an operation cannot be represented with the available hardware. So if you have 2 to the 31 minus 1 and you're adding 2 to the 31 minus 1, it's not going to be able to be represented because you're going to get an overflow value, right? So you can't represent it using this hardware. And so here's another example. Subtract 1 from 2 to the negative 31. So what we would actually do, sorry, that's add. Hold on. When adding operands with different signs, overflow cannot occur. This is the same when you're subtracting two numbers with the same sign. So think about it this way: if you had if you're subtracting two numbers with the same sign, so if it's 10 minus 6, it's not possible to go over 2 to the negative 31, right? If you had negative, right? An overflow is possible when adding operands of the same sign or subtracting numbers of different signs. This is because when the numbers exceed 31 bits, the value of this 32nd bit becomes overwritten, changing the value of the sign. So in this case, and this is where the criticism of what I have here is actually valid. So in this case, what you're doing is you're adding. So this becomes, yeah, so subtraction. So basically what you're doing is, that's fine. Subtracting 1, so that becomes here. So basically all you're doing is you're subtracting this value. So that example is there to show you that you can't get overflow when subtracting two numbers of the same sign. Because if you have, let's say you're subtracting two negative numbers. So if you're subtracting negative 2 to the 31 minus negative 2 to the 31, it becomes an addition, so you end up getting 0, right? So you can't exceed that. However, when you add 2 to the 31, right? What ends up happening is you get carry bit, 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 and that second gets overwritten. And as we defined in the topical guide objective earlier, this actual number is negative 2 to the 31, right? So instead of getting 2 to the 31, we're getting negative 2 to the 31. So we're getting the incorrect value, which means we can no longer physically represent the value in the architecture. Does that make sense? Oh, I remember, to answer your question, I remember why I did that. So the reason why I did that, a lot of the things that I do here are because of issues that arose in previous iterations of the class. So when I did that last year and didn't have a sign, people kind of freaked out, like, wait, should I be 2 and 2's complement of the 2? Like, okay, fine, I'll just put a subtraction sign there to make everybody feel comfortable. And then what ends up happening is then students don't feel comfortable because they suddenly see the subtraction sign. So sometimes you just can't win. I was like, Thomas Pitts, I remember you. All right, so that's all well and good. So the question becomes, how do we actually detect overflow? When you actually get one of these overflow situations, it's all well and good that we know that it shouldn't happen, but when it does happen, what do we do? there needs to be some sort of physical hardware detail to indicate to the computer what needs to be done. I'll get to your question in a second. So typical guide objective 2.4 is an exception is an unscheduled event that disrupts program flow, meaning that we have in some way, shape, or form recognized that either we do some shifting or we've done something in the arithmetic logic unit that indicates that the value that was calculated is wrong. And we know this, and we need to do something, and it's typically done at the operating system. And so, if you're familiar, if you ever, you all seen the blue screen of death, right? Or you're at least familiar with it. So, if you see in the blue screen of death, it tells you that there's an unhandled exception, and then you see 0x, and then some giant hexadecimal number. So, what that is, and we'll learn about that later in this course, is that there's some sort of calculation, it went wrong, and then those of you who coded in Java or in C++, you're familiar with try-catch blocks. So the whole idea is you do some sort of operation, and if it doesn't work, you go to the catch block, and the catch is supposed to say, hey, this screwed up, we're going to stop the program, you need to fix this. The blue screen of death is what happens when no program catches the exception error. And it's like, we got to just shut down the whole computer. Something's wrong. And that hexadecimal value is where the instruction that went wrong is stored. So that when the operating system starts back up, it reviews what happens to figure out precisely what needs to be done.
That would be a register address?
Yes. It's a specific register address, and we'll get to it later in the class, called the error program counter. All right, so what's your question?
You actually already answered it. I was just wondering how much you want to take out 2.4.
2.4 is define exception. Typically, if you don't see an end here like what I have here, not typically, in every case, if you just see TGO 2.4 and you don't see an end, that means it's just that line. That's typically reserved for definition. So in this case, define exception, an unscheduled event that disrupts program flow. Oh, and to get to what the exception program counter is the register. So I have a whole paragraph on that here. So this will be this will make a lot more sense. So there's an actual move from system control instruction, which stores the result. So RD, there's RS, RT, and RD. RD stands for R destinations, if you remember that addition earlier. So you have two registers and store them in a destination register. So basically it's saying this destination register is supposed to store a result. However, the value that we've calculated to store in it is wrong. I need to know when I finally get a correct value that we fixed it using our troubleshooting, either the operating system or some sort of insertion of stalls. I need to know where I need to put it when I'm done. You can think of it as a placeholder. And so, in order to deal with this, we also want to worry about what happens when we want a number that's larger than 2 to the 31 minus 1. A lot of times you'll be using those for scientific calculations, right? So if you recall from middle school and high school, you remember scientific notation? So you had 2.31 times 10 to the negative 18 moles or whatever, right? So you wouldn't write 0.00000000, going all the way to this and then 231 at the end every time, because that becomes cumbersome. Well, it also in the case of the computer architecture and the computer organization, you're limited in RISC to 32 bits. In the case where you need to do calculations that require greater than 32 bits, we want to use floating point notation. And the specific, before I get into that, does anybody know what IEEE stands for?
Institute for Electrical and Electronic Engineers.
Yes. So IEEE manages standards. So the IEEE 754 format is a standard that is specifically designed for how a 32-bit floating point architecture is done. So this is going to be common in any 32-bit architecture you want. So in this case, the first bit is going to be the sign bit. So what you're basically going to have is you're going to have the first bit, then you have the next 8 bits are going to be your exponent, and the next 23 bits are what's going to be called the mantissa. And so to relate this to your, we'll go back 2.13 times 10 to the negative 18, right? So we have a sign bit here that indicates positive or negative. So if this was negative, we'd have this. So the reason why it's 0 is the notation for positive is when you're writing this out normally, notice how there's nothing there. You just naturally assume that it's positive if you don't see any signs. So they kept the same notation as everybody used while doing handwriting to say no sign is positive. And then if there is a sign, it's typically, we use that to indicate it's negative. So that's why the sign bit is 1 for negative. So in this case, the IEEE format is a format used to track large floating point numbers using a 32-bit number. So we have the same constraint, but then we're going to be using that to represent numbers that are bigger. So then the next 8 bits are the exponent. So what is the value of 2 to the 8? I hear it. Someone say it loud and proud. 256. Okay. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 4, 8, 16, 32, 64, 128, 256, 512, 1024, right? So those are the first 10. So 256. And so the other one number you want to know is 128 here. So here's the question. If I want to represent both positive and negative exponents, right? The example I gave you for scientific notation was 10 to the negative 18. So how do I represent a negative number if my range is only 0 to 255? No. The sign bit represents the sign of the actual number. It's a good guess, but no. Any ideas? No, we are limited to 32 bits, and we're limiting the exponent to 8 bits. So how do you actually? So this is where your design constraints come in. Your design requires good compromise. All right, so let me think for you. So that's far more complicated than you need. Make it simpler. I'll give you a hint. Compiler-driven encoding of the microarray. So here's what we're going to say. We're going to define the 0 through 127 as negative integers. And then 128 through 255 is positive. We're just going to have a range of them that the computer knows from the compiler. And so we're going to calculate that by saying the exponent value minus 127 is the actual exponent. So if it's 255, which is actually going to be 255 minus 127, which is equal to 128. So it's actually 2 to the 128. So if the exponent is 3, it becomes 3 minus 127. So therefore, the value is actually 2 to the negative 124. And so you just allow the compiler to drive that for you. So that reduces complexity of the design. Does that make sense? So what ends up happening here is the first bit is the sign bit of the whole number, and then we use this value to calculate the exponent, and then the next 23 bits are what we call the mantissa. Now, the reason I include this in the topical guide objective, the 1 plus mantissa is used to normalize the number just like scientific notation. So if if you had 0.131 times 10 to the negative 6, right? We can, the normalizing process is we make it 1.31 times 10 to the negative 5. So what this means is that since we know that the values can be 0 or 1, we shift the mantissa until we find that first one, and then everything after that is what's stored, because that allows us to save 1 bit of space. So I'll give you an example here, TGO 2.6. But basically what's going on here is, let's say you had, 0.5 is a perfect example. I want to store 0.5 as a floating point number. So 0.5 is actually 0.1000000, right? So what I can do is I just shift it over, I normalize it, so it becomes 1.0000, because that's our first bit there. And then the mantissa is just 0.00000. So this is actually 1.0000 times 2 to the negative 1, right? So 2 to the negative 1 is actually the solution to that equation, right? So then we just need, what is the value of E that makes that negative 1? So what is that value? I heard somebody said it quietly. 126. So then 126 is just simply 0, 1, 2, 3, 4, 5, 6. Right? It's going to be, when I do this question on the exam, it's going to be 126 or 1 through 128. It's going to be in that range. So it's either going to be that number, or that number, or 1, right? Some sort of plus 0, plus 1, plus 2 from the 127. Because this number is 127, so that's, you add or subtract. It makes it simpler than doing 234, and then suddenly you're doing something that you should have known how to do in 235, and I'm not testing you on 235 material. So same thing if it was 0.6125, right? Well, that translates out. So 0.5 is 0.1, and then 0.0125 is actually 001, right? So that's times 2 to the 0. We normalize it, 1.0010 times 2 to the negative 1. That becomes, E is now 126. The mantissa is 0010. Sign bit is 0. So then our actual value is going to be 0, and then the exponent is 0. It's 126. And then it's going to be 0010. And then I ask you to write the first 4 bits, and then what you'll see when in the example questions is I don't want you to write the rest of the 23 bits. I just want to say for 23 bits. ... That'll save you. You do need to demonstrate on the exam that you know that it's 23 bits long, but I don't want you to write 23 zeros. Okay, so does anybody have any questions about that? We're going to go over a few examples here. Okay, so these values of 2 to the negative, 2 to the 31 minus 1 and negative 2 to the 31. When we want to talk about positive and negative infinity, we're going to use floating point. So here we have exponents, sign value, and then we use positive values in the floating point to represent the results. So in this case, we have negative 1 to the 1 times 1 plus 0. See that? Times 2 to the E. So E, this is, what is that value here? If I have 8 ones, what is that number? 255. 256 is 2 to the 8. So this is the reason why I wanted to go over this here. You have 2 to the 8, which is 1, and then 8 zeros, right? So what's going to happen is, you think of it the same way. 2 to the 1 is 1 0. You see that? So what ends up happening is the number of bits represented in the exponent just happens to be 1 less. That's the way it works out. So what ends up happening is the number of bits, so 2 to the 8th minus 1 happens to be 1, 2, 3, 4, 5, 6, 7, 8 bits, like we have here. And that's 256 minus 1, which equals 255. So at the smaller scale, 2 to the 1 minus 1 is 1 bit, just like this is 8 bits. So that just becomes 2 to the minus, which is 1. Sorry, that's base 2, and that's base 10. See how that worked out? That's just the simpler version. So 8 bits total. This is what they're representing infinity is negative 1, negative 2 to the 255 is negative infinity, and then positive is positive infinity. So for example, if you're doing the topical guide objective, you can just write the first 4 bits and then say ... for 23 bits. That should save you some writing. And you do the same thing for 23 bits. Does that make sense? It's something I'm going to emphasize when you take the first exam, is that learning these binary values and being able to do some of the simpler ones quickly off the top of your head. In this case, example 2.1 is a good example of how you do this. So, I know I just gave you the solution to it, but how do you actually calculate that out using IEEE 754? So you start out, the first bit is our sign bit. So if you recall from the equation, it's negative 1s. So you're just actually taking the bit value and putting it there. So it's negative 1 to the 1. So it's a negative number. Plus 1 plus the mantissa. So in this case, the mantissa is 0. Right? So it's 1 plus 0 times the exponent. So it's e minus 127. So in this case, e is 255. 255 minus 127 comes out to 128. So just negative 2 to the 128, which we represent as negative infinity. Does that make sense? That's the simple version. So here's the one that's a little more complicated. I'll zoom in for you. So part B, we have this exponent here. We have the sign bit here, and then we have this mantissa. So how do we do this? Sign bit is 0, comes here. This value, if you see this, it's actually 128 plus this value here. So to make this simple, 128 plus 3 is 131. So in that case, we put 131 minus 127. So you can see that comes down here. I'm sorry, this is 128 plus 128. Oh no, that's 128 plus 5. I was like, what? That's 5. So 128 plus 5 comes out to 133 minus 127, which is going to be 6. So that comes out to 2 to the 6. Make sense? So this value is 0. It's going to be 1 plus, and then the number you need to figure out is 0101 here, right? So do you all know how to convert this number? In the past, students have not known how this. That's perfectly fine to say no. I saw a lot of people shake their heads no. So let's do it. Let's learn how to do this. 0101. So if you recall, if we were doing 101 base 2 to a positive number, this would be 2 to the 0, 2 to the 1, 2 to the 2, right? So this would be 1, 0, and 4, which is 5, which is what I screwed up earlier. Somehow I made that 3. Don't worry, I make fun of myself when I make mistakes. It's fine. But how do we do this in 0.0101? So here, this is 2 to the negative 1. 2 to the negative 2, 2 to the negative 3, 2 to the negative 4. So what is 2 to the negative 1? 1/2, which is 0.5, right? So this becomes 0 times 0.5, right? Plus, so it's 2 to the negative 2. 0.25. So this becomes 1 plus 0.25. So what's 2 to the negative 3? So this becomes 0 times 0.125. And then the last number is 1 times 0.0625. So that's as far as I'm going to want you to know off the top of your head, which is why on the exam, any of these problems will be limited to 4 digits. So this becomes 0.25 plus 0.0625, which comes out, after you practice this enough, it'll be 0.3125. So that's your mantissa. It's 0101. So if it was 1010, it becomes 0 plus 0.5, right? Plus 0 times 0.25 plus 1 times 125. So it becomes 0.6125. Does that make sense? So we'll work through several examples, and then as you're studying for the exam, you'll actually be able to, as you're starting to create your own exam, you'll see that when you limit this, it becomes, you start to be able to practice it better than you intuitively understand. If it comes out to 0.11, like, oh, okay, good, you'll actually know it without having to do the conversion. Yeah, the mantissa is this number here. So then as the IEEE 754 standard states, and this is, I think this is where you're going with your question, is it's 1 plus 0.3125 because it's been normalized. So that becomes 1.3125 times positive 1 times 2 to the 6th, which is 64. So in this case, on an exam, and this is something I should note here, on an exam, if I were to ask a question like this, that's a correct answer. Because from there, either you're going to give me a still correct answer, or you're going to put it in your calculator wrong and lose points. So from here, there's no added benefit. And obviously, I'm not here to grade you on how you can punch numbers into a calculator, right? That's not why you're in this class. So if you actually show me the steps and you do a representation, actually, if I want to be technical, I would give full credit for this too. That demonstrates to me that you know how to convert to binary, you know how to set up the IEEE 754, and that you know how to connect the binary and put it correctly into the exponent in the equation. So this is a full-on 100% correct answer on an exam. You wouldn't even need to do this. But if you wanted to walk through it, when we're actually representing is the number 84. Does anybody have any questions about this? All right. Okay, so for the rest of today's lecture, before we get into actual like floating point addition and subtraction, I want to get into what actual physical details are going on when you perform an addition. So addition, does anybody not recognize this full adder circuit? All right, I'd be happy to explain it then. What's going on here is you have a full adder, you're adding 2 bits and you have a carry-in bit, right? So in this case, you can have 1, 1, and 1, right? So you're adding these 2 values and you're getting a carry-in from before. So you can either get 0, 1, 2, or 3. So what's going on here is that the actual equations which is this topical guide objective here, comes out such that it's A XOR B XOR the carry-in is what's known as our sum. So if we had 3, it would be A XOR B XOR C, which we would want our sum value to be 1, right? And we want our carry bit to be 1, which means we're actually carrying another value. So the whole point of a full adder is you're actually determining if it's the carry bit is 0 and A and B are both 1, then the sum is going to be 2, which means the sum should be 0 and the carry bit should be 1. So A XOR B, if both of them are 1, it's going to be 0. Does that make sense? And the carry out, physically, it's A XOR B, which we see here is the same thing. And then it's ANDed with the carry in bit. And then we also have an AND here, A and B, and they're put into an OR bit for this carry out. So that logic is indicating whether or not we want to perform this. So if we have, if it's an 8 value truth table, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? So the sum, so we're going to do carry and sum. So sum is just going to be A XOR B XOR C. So this would be 0, 1, 1, A XOR B is going to be 0, right? And then this value, A and B, so Cn is all 0 here. So this just becomes A and B, so that becomes 1, 0, 0, and 0. So you can see 1 and 1 becomes 2. And then here, 1, 0, 0, 1. So here it's 1 plus 0, 1, 1, 1. So that's how that physically works out there. So that's a 1-bit full adder. So it allows us to add 2 1-bit values with a carry value. And so if you're thinking about it the same way you're doing addition when you're starting out, let's say you're adding 10 and 16. So here, you would actually be using a full 1-bit digit adder where your carry value becomes 0. Let me make this 9 and 4 so we can do a better example. So this becomes 14 and 19, right? So you have a carry-in of 0. You get 4 plus 9. The sum bit is just equivalent to 3, and then the carry bit becomes a 1 over there. So then it becomes 1, 1, and 1. So you have A, B, and carry. So that becomes, in this case, it becomes 3 because you have a digit. If you're doing this in each physical value is being done with a carry bit over there. So it becomes 1, carry 0, carry in 0, 1, 1, 0, 1. Yeah.
So could you have a circuit that ignored or didn't take into account the carry bit and have like a partial adder? Like does the term full adder like? No,
well, the full adder, you're actually talking about how it's split up into pieces here, right? So there is a partial adder device, right? So you want to combine them together to get full adder. But the full adder does the full range of addition. And the reason we want to know this is because you can then use 1-bit full adders and other logic devices to build a adder of any number of bits. So this is your fundamental device that you want to use for building an ALU in a computer architecture, in an advanced digital system, I should say. Okay, so 2.8 is now if we have a full adder, and instead of adding a lot of overhead, there's a device called a full subtractor. So let's say I want to design an ALU that does addition and subtraction. And so remember MIPS, the whole idea of MIPS is high performance execution of compiled code, and which means we want it to run fast. And so if you have a lot of area overhead, it'll run a lot slower because it requires more control units. So there's actually a way of doing this. So how you do this is instead of including another full subtractor for, let's say I have a 32-bit ALU. Instead of having full adder and another full subtractor and have 32 of those. What I can do instead is just invert all the values of B. So what I would have is just one bit come in, and it would be all attached to XOR gates. So B would be coming in. If it's 0, it just means addition. So then if you're not XORing, anything XORing is 0, we'll just pass the value. If it becomes 1, it becomes a glorified inverter. So instead of adding a bunch of full subtractors, you just add one XOR gate at the input of B. So you invert all the values. So this gives A plus not B. And then to obtain 2's complement, we have A plus not B plus 1. So therefore, using the initial carry in bit as a 1, that performs our 2's complement for us. So if we have one bit that we want to pass on to all these XOR gates and a 1 bit that we want to use as a carry-in, what we just do is we just use that same bit value, put it into the carry, and then put it as the input to all the XOR values. And so what you notice here, use XOR gates for each B input. If so the control signal add/sub is 0, no B inputs are changed. And if add sub is equal to 1, then all B inputs are inverted. And then use add sub as the initial carry in bit. So you're doing that as the 2's complement. And what you'll learn later is that if you remember those last 6 bits of the function from the machine code, what you'll see is that 1 0 0 0 0 0 is addition, and 1 0 0 1 0 0 is subtraction. So what that means is this bit that's different, that becomes your actual input into your carry bit, as well as the input to all the XOR gates. So you're actually able to use the actual instruction's function value to significantly reduce the area of the design. So you cut the adder subtractor area in half, essentially. Does that make sense? So this is a great example of how you can use designing an instruction set architecture while knowing the physical details of the arithmetic logic unit to improve the performance of the code and of the machine. Does anybody have any questions on this? Because the next TGO is actually a drawing of the of a 4-bit add subtract logic unit. And so here it is. Okay, you can see it really well on the screen here. So you can see here that we have this add sub bit input, right? And so what's happening is it goes into each XOR gate like so, as well as the carry into the first full adder. So FA there is full adder, right? And then everything else just goes into the full adder as is. Now, normally what you would, if you wanted to do this otherwise, you'd have to add a full subtractor and then split each input to go there, right? So what you've done by reducing this design and then taking advantage of the machine instruction and instruction set architecture is you cut this area in half. So here you add sub, you have the carry in / borrow, and then you just perform full addition like you normally would. And then the outputs come out as normal, and then the carry / borrow bit comes out at the end of the end here. Give everybody some second to jot that down. So does this make sense to everybody? Is there anybody who this is struggling with this?
Doesn't it always go like the last bit would be your sum 0?
Mm.
So it always builds from like the left.
Right. What's so you have the let's say I'm subtracting 1 1 and 1 0, right? So then I carry in there. Yeah. And so the previous topical guide objective is the mathematical proof that this works, and then this is the physical outline. Okay, so I'll scroll up a little bit here. So you have a 32-bit. So this is basically an example of what's known as a ripple carry adder. So you do the initial one, and then it ripples a little further, and then ripples all the way to the last bit. And so if this is the slowest addition. So there's a lot of research going into different types of adders. We have what's known as a carry select adder. The whole idea of a carry select adder is that you're going to add an area. So what's going to happen here is you perform the initial 16 bits of addition. And then what's going on here is you're taking these 16-bit values, and this first portion of the adder is what will happen if we assume that the carry bit is 0. And then we do the same thing, bits 16, 30 to 31, but we assume if the bit is 1. So we're actually performing these values here. We're not just waiting for them as we do in the ripple carry, right? And so what ends up happening is this carry out bit serves as the input to a multiplexer, which allows it to do this decision. Now, this is, some students actually done this. Who does not know what a multiplexer is? Okay, got a couple people who don't know what a multiplexer is. So what a multiplexer is a device, the logic device, which takes in 2 or more inputs. So let's just call this input A and input B. And then using a select value, puts the value on the output. So if you'll see 0 and 1 here, right? So if the input is 0, it just puts A. And if the input is 1, it'll put out B on the other side. So what will end up happening, you'll see this when we have to make decisions, is you'll see 0 and 1 and 2 like 5-bit inputs to decide which register I want. And then based on a control signal, it'll put a 5-bit value on the output. So you see that a lot when we get to the data path design. So what's going on here is it's actually, we know that this carry-in value is going to be either 0 or 1. It has to be. So this is the result if the carry-in value is 0. This is the result if the carry value is 1. And then they both get there right as this value is being calculated, because they're being calculated at the same time. And then we use that as the decision. So if it's 0, well then this is the value that we wanted to calculate. So it just pushes this value out as some bits 16 to 31. So it cuts the calculation time in half. But what's the trade-off? I've improved the performance of the device by 2, but what did I add? I have to use more power is thing, but the key thing, the actual answer I'm looking for is more area, but what you said is absolutely right. Because if you have more, this adds more silicon. So you're adding more silicon here, which means you're adding more area, adding more cost. And if you have 3 of something consuming power instead of 2 of something consuming power, you are also adding more power. So, and then there's actually full-on carry look-ahead adders. So we're not going to really go into those in much detail in this course, but I think we'll end with TGO 2.10. So it'll be TGO 2.1 through 2.10 of the example problems we've done up so far. So for those of you there's probably some of you in here who are not familiar with big O notation. Does this look like gibberish to some of you? Okay, so that's why I want to end here so that way I can give it a fair explanation what big O notation is. Big O notation is basically a description of how long an algorithm will take. Now, there's a whole algorithms course, and for those of you who are computer science, I know that what I've said is extremely basic, but it's sufficient to understand what's going on here. So, ripple carry has a slower execution time, big O of n. So what big O of n means is that I have a 32-bit value, or a 64-bit value, or a 16-bit value, right? I have to perform 16 full adder operations before I have my value, right? So the big O time is n, meaning that I have to do n operations. But it has a smaller space complexity, which means I need n full adders. So that's what big O of n is here. So carry select has an improved execution time. So we're cutting it, we're getting the square root of it there, but it has a slightly larger space complexity because we have to add that extra area. Does that make sense? Now carry look ahead is a very complex form where you have to add a lot of area. So it becomes n log n, n times log n. So we have 32, right? So what's, does any of you know what log 2 of 32 is? 5. Is anybody confused where I got that number? I have no idea where I got, everybody knows how I got it. So basically it's just 2 to the 5th is 32. So if I said log 2 of 128, that's 7. 256 is 8, so forth. So n log n means my area complexity is 32 times 5. So I'm now adding a lot of area, but it's running extremely fast. So if area in the ALU is something that I don't care about, suddenly your manufacturer might be okay with that. They're like, whoa, costs matter more. Then you have to do some sort of salesmanship and trade-off between ripple carry and carry select. Does that make sense? And before I dismiss you, I know it's 10:45. One of the reasons why I emphasize these trade-offs so much, let me give you an example of a research project I'm doing. There's a recent study came out that said 85% of Internet of Things developers have felt pressure to rush a device to market despite security concerns. And the reason why that is that security requires area, sometimes requires power consumption, sometimes requires additional processing capability. So if you ever end up in one of these situations where you feel uncomfortable about a device and you need to go to your manufacturer, these concepts, well, we're going over them more simply here in this course, will allow you to make more informed presentations to your manufacturer in the event that you feel that something isn't ready to go out to market. So this is why I emphasize this very heavily in this course. So on that note, I will let you go out, and I will see you all on Thursday.